When it comes to the veins, if I start my journey here again, I have elastic arteries, muscular arteries, arterioles, a meta-arterial, into the capillaries or the capillary bed. And now I'm going to go back to the heart. I've dropped off all the oxygen, picked up all that CO2 and waste, got to go back towards the heart. So now I go back towards the heart and I go into the first venule structure. And these are venules. These are very small veins, very, very, very small veins. They're about 8 to 100 micrometers in size. They ain't that big. Okay, they ain't that big. They are the companion vessel, if you will, of the arterioles. Remember, arteries and veins run together. Where you see the artery, 10 times out of 10, you see the vein running with it. Okay, so if the arterial is leading into that capillary bed, what leads away from it is the venule. So it's the companion vessel. That's what I mean by that. Some of your smaller venules will have a little capillary there, or I'm sorry, have a little post-capillary sphincter to kind of govern, again, that thoroughfare channel to allow it to be bypassed, but who cares? I mean, that's not huge. Venules can have, as they get further away from that capillary bed, they can have all three layers, all three tunics, but I mean, you're talking like this. There's one. There's the next. And there's a single layer the next. So, I mean, they aren't really thick. They aren't that thick at all. All right. As the venules get further away from the capillary bed, they merge and form small veins. As small veins get further away from the capillary bed or closer to the heart, they merge and become medium-sized veins. As the medium-sized veins merge and get closer to the heart, they become shockingly larger veins. This isn't really mentally tough, at least I hope not. Small and medium-sized veins are companion vessels with the muscular arteries. The largest veins travel with the elastic arteries. Not heavy-hitting stuff. It is these medium-sized veins and small-sized veins and large veins, all of them though, they do have valves. If you don't have a big tunica media layer and you can't do a huge amount of vasoconstricting and vasodilating, the only way that we can ensure that blood goes forward through the system is to put a structure inside of them to prevent that backflow of blood. Here comes the valves. All of these small, medium, and large veins have valves within them, and it prevents blood from pooling and ensures that it goes forward through the system. It's basically the tunica intima layer in a valve-shaped form. And like I said earlier, I'm not going to ask you the numbers, guys. I'm not asking you the numbers. It's there to show you that the vast majority of systemic circulation, of systemic blood, is going to be housed within the veins. Why are they housed within the veins, you ask? It's because they have a little muscular layer and a very large lumen. So they can expand and accept a huge volume of blood. And they have a tendency not to constrict when getting fed more blood. And, you can see, the breakdown there, 55% is systemic veins, which is the vast majority of the remainder of it. So the vast majority of blood in the system is in the veins. You can see 18% of the blood to the lungs, 12 to the heart. I don't care, to be honest. I just want you to know that because these veins have a very large lumen and not a big tunica media layer at all, they accept a large volume of blood. But that's great. That's great. I can shift it back and forth, okay? There is a little bit of there is a little bit of tunica media in those veins. So they can constrict a little bit And just a little bit of constriction helps to shift blood back into organs if need be. Let's say you are getting up from a seated position. You're going to need more blood, to go to the brain. So the blood vessels will constrict a little bit and you'll have more reservoir, more reserves, if you will, for blood to be shifted to go to the brain. If you become active and start, walking around, that creates a metabolic demand by the muscles. So what do they do? What do blood vessels do? Well, those veins constrict a little bit. And now I can get that to go to where the physiological demand requires it. So that's the great takeaway for the blood reservoir concept, is that just a little bit of vasoconstriction by those blood vessels, by those veins, I can shift blood and increase the amount of blood within the arterial system. And what does that mean? Organs that need it, like muscles, when you start to get up and move around and be active, metabolic demand increases dramatically, as opposed to just sitting here. Okay. So I can get that blood readily from into the arterial system and in the arterial system into the muscles. And I don't necessarily have to, create more blood out of thin air. Okay. So that's the importance of that blood reservoir concept. The last thing to kind of think about when it comes to arteries, capillaries, veins, there are multiple pathways through which blood can be delivered or blood can be taken away. The most common way that we think of is the simple pathway. Okay. I have an artery that goes into a region that goes and delivers blood to a specific structure. It branches and branches and branches as you get further away from the heart or closer to the organ. And that artery becomes an arteriole, and an arteriole becomes a meta-arteriole, and meta-arteriole feeds the capillary bed. Okay. And then we leave through the venules, small, medium, large. Boring, right? Simple pathway, easy pathway. There are a number of alternate pathways, though. And I've kind of been mythically mentioning them, talking about them without saying the words. All right. We saw one with that thoroughfare channel where we have this shunt, where we take it from the arterial side to the venous side directly. This allows blood to bypass an area when situation demands it. Too much pressure, too cold. You go outside on a cold day, what happens? Vasoconstriction. Getting blood away from the periphery and getting deeper into the body to keep your core warm. Well, your fingers and toes, they get really cold, don't they? If you don't wear gloves. Any of those structures get really cold, right? We are shunting blood away from those. They're still getting some. They're not just perfused or coursing with blood. And then what happens when you go inside? Especially in your cheeks, right? You notice they get all red and flushed. Why is that? Because it's cold as hell outside. You went inside, it's really warm. All of a sudden, I have some really reactive hyperemia. Blood gets into those regions where it was constricted, right? If I've been constricting blood, what's been building up? Metabolic waste, hydrogen ions, potassium, all the metabolic waste. So I got to get more blood in there because I got to get more oxygen in there. It's been deprived of oxygen. I've been vasoconstricting. So I got to get more blood in there. So all that blood floods the region right there and you get all that red, rosy appearance in those cheeks. Same thing with your fingers and toes. When the blood gets shunted away from them, they get really super cold and they get really white. When they get really warm, they get more reddish in color, more blood perfusing those regions. How can we bypass all that? That's what the shunt does, the arteriovenous anastomosis. And anastomosis just means more than one, okay? So if my head is the organ, I have 3 different blood vessels through which I can get blood to it. Take that blood vessel away, and I have blood that can go through the bottom 2 fingers and then up to the top. Okay, that's the great thing about anastomoses. We have arterial anastomoses, the superior and inferior mesenteric artery. One supplies blood to the upper half of the intestinal system within the abdominal area. The inferior does it to the inferior aspect. If you block the superior mesenteric artery or have some kind of blockage within that, it can, through a roundabout way, get up there. Takes a little bit of time, but it can. And I can still perfuse those regions with some blood. Is it optimal? No. But can it supply it with a little bit of blood? Yes. And there's really a few of these that are very obvious within the body. The ones within the digestive system, ones within the brain. You have one, that's probably the most common, the circle of Willis. Trying to think of some other obvious areas of arterial anastomoses. The heart, pituitary gland. So there's some. The other one we have is a venous anastomosis. And if you already know what arterial, put vein in it instead of artery, and you know it's veins. Multiple veins draining a body part, body region. The veins in the upper arm are a classic example of that. Basilic, brachial, and cephalic. Basilic is draining this half, the brachial, the outer half, and the cephalic, the outer half, and then the brachial is the middle aspect. So these 3 blood vessels all drain the medial, anterior, and lateral compartments of the arm itself. It takes all 3 of them to do that. That would be a venous anastomosis because they all drain up into the subclavian vein ultimately. And here's that shunt bypassing, okay? An arterial anastomosis, a venous anastomosis, okay? And then our last alternative pathway is a portal system. The hypothalamus pituitary, the hypothalamo-hypophyseal portal system. That's what this is. I'll just write what those words mean. Hypothalamus, pituitary gland. Okay, that's what that is. We have one within the digestive system as well. So there's more portal systems. But portal system, multiple capillary beds in a sequence that really supply everything. And in no better way do we see that as that example down there. But there are alternate pathways. It's just not one blood vessel in, one blood vessel out. It's not generally like that in all places. Okay.